In this lecture we're going to talk about simulation, bootstrapping and Monte Carlo. And all of these three methods are types of simulation methods where we use lots of random numbers to explore distributions, probability distributions. And we can use this just to understand better how these probabilities work or how particular models work. We can use it, for example, to improve our intuition about how sampling works, how estimation works, etc. We can use it to explore probability distributions, where just knowing the mean and the variance is sometimes not enough to fully understand what it looks like, especially if it's a more complicated probability distribution. And most importantly, we can use it to get proper uncertainty estimates for quantities where this is not straightforward to derive. So for example, when we estimate a regression, we straightforwardly know what the standard errors are on the beta distribution. We have analytical solutions for that. Sorry, the standard errors on the beta estimates. But for example, if we have a predicted probability from a logit regression, it already becomes harder to get good uncertainty estimates. And simulation and bootstrapping can really help there. Note that because all these methods use random numbers to generate their output, if you're going to run the same code twice, you're going to get slightly different answers each time. These are not predetermined, analytically fixed outcomes. On this slide is the basic idea behind simulation and bootstrapping. For simulation, we first estimate our model, and then we get estimates for our coefficients. And especially in the maximum likelihood framework, we know that these asymptotically have a normal distribution. So we get a multivariate normal distribution of all the coefficients in the model, and that on average are the estimated coefficients, and where this distribution has a variance that depends on the standard errors. So if we want to calculate some quantity that is not standard part of the output from a probit or logit regression, for example, say the predicted probability of a particular outcome, then we can take the estimated beta coefficients and use this to calculate the predicted probability, as we've done in the previous class. But if we want to have a better assessment of the uncertainty, instead of taking the estimated beta coefficients, we can randomly draw a large set of beta coefficients from the estimated variance-covariance matrix of the betas. So instead of just taking the optimal value that maximizes the likelihood function, we take into account the uncertainty around our beta estimates and draw a lot of different beta values that on average that will typically be close to the estimated beta coefficient and occasionally be much further away. And each time we use those new sampled beta coefficients to calculate the predicted probability, and then we look at how these predicted probabilities vary to get an assessment of how the uncertainty in the estimates of the beta coefficients now impact on the uncertainty of our estimated predicted probability. So we assume that we know the distribution of beta. We have estimated beta, we've estimated standard errors on beta and the full variance-covariance matrix of the beta estimates. And we assume that this has a multivariate normal distribution. And we then use these estimated values of the variance-covariance matrix to sample different values of beta and calculate predicted values. So this makes strong assumptions about the distribution of these beta values. We have to be correct that it is a multivariate normal distribution, that we correctly estimated the variance-covariance matrix. Otherwise, these samples don't tell us much. Bootstrapping is a procedure that is going to be slower, it's computationally more intensive, but it makes weaker assumptions about distributions. In bootstrapping, we repeat the whole estimation of the model over and over again. So where in a simulation we estimate the model once and then we sample lots of betas from the estimated values of beta and the variance-covariance matrix. In bootstrapping, we randomly sample from the original data set and then re-estimate the model each time. If it's a computationally intensive model to estimate, for example a complicated multi-level model, then bootstrapping is going to be very slow. But bootstrapping makes fewer assumptions about the distribution of estimated parameters, and therefore it translates uncertainty a little bit better. So in bootstrapping, we take a random sample instead of the original sample, and this random sample is taken from the original sample, and it's also of the same size as the original sample. And by sampling with replacement, that means that the same observation can be sampled more than once. Despite the fact that we take a sample from the original sample of exactly the same size of the original sample, we do each time get a very different sample, because several observations will be sampled multiple times and other observations will not be sampled. So it has been shown mathematically that if you take bootstrap samples from an original sample and you calculate a statistic on each of these bootstrap samples, and you look at the distribution of this statistic across bootstrap samples, that this distribution will approximate the sampling distribution of the statistic for the original sample relative to the population. So let's first look at the principle of simulation, or rather simulated parameters. Strictly speaking, all the methods that I'm discussing in this week, simulation, bootstrapping and Monte Carlo, they're all forms of simulation. Here we're talking about simulated parameters. So we estimate parameters of the model that maximize the likelihood of that model, but then we simulate by sampling parameters from the estimated probability distribution of these parameters. So for example, when we have OLS estimates, we don't only estimate beta, we also estimate the standard errors, or rather the full variance covariance matrix, where the square root of the diagonal of that matrix are the standard errors. So the variance covariance matrix shows you how much uncertainty we have around each of the betas and how this uncertainty is correlated between the different betas. If one beta is in fact a bit higher than what we had estimated, then another beta is going to be a little bit lower, for example, if they are negatively correlated. Because that then improves the model fit. So these different uncertainties around the betas, they're not independent. So we have a multivariate normal distribution of beta parameters, or if we've estimated the error variance, we have a multivariate t distribution. And we can sample from this distribution to get sampled parameters and use these to calculate estimated quantities. For example, predicted probabilities, or etc. And similarly, with maximum likelihoods, we know that asymptotically the estimated coefficients will have a normal distribution, and we can use the square root of the negative inverse of the Hessian matrix, for example, as an estimator for the variance covariance matrix. And again, we can sample from this multivariate normal distribution to get a set of sampled parameters, and for each of those sets we calculate the quantity we're interested in, and then we look how this changes across these samples to get an estimate, an assessment of the uncertainty of our quantity of interest. So here's a simple example from a logistic regression. We have an estimated beta of 0.4, and for a particular value of x, say x is 3, we can calculate the probability of that y is 1 by filling out this simple logistic equation. Yeah? And so we get a predicted probability of 0.77. However, when we estimate the beta, although our best estimate is 0.4, we have a certain level of uncertainty in this estimate. And so there's a standard error associated with it. And now we want to know what the standard error is around this predicted probability, 0.77. So we can sample many betas, always taking into account the standard error. So we sample from the normal distribution that is given by beta and its standard error. And then each time calculate this predicted probability and then see how this varies. And that will give us a sense of the variation of the uncertainty of this predicted value. The best here is probably to calculate a 95% confidence interval. So we calculate for each of the simulated parameters, we calculate the predicted probability, and then we disregard the highest 2.5% of those estimated probabilities and the lowest 2.5%, and then the range that we are left with is our 95% confidence interval for the predicted probability. So this slide summarizes these steps one more time, assuming a maximum likelihood estimate. So we estimate our model, we obtain an estimate for our beta values, but also a Hessian matrix. We can take the inverse of the Hessian matrix and the square of the negative inverse of the Hessian matrix. That will be our estimate for the variance covariance matrix. And then we can sample many times beta values from this multivariate normal distribution. And for each of those samples, we calculate the quantity we're interested in, for example, a predicted value. And then we look at how this varies. For example, by looking at the 95% quantiles. So this slide shows how to do that in R. So it shows you how we can estimate a particular model with Optim, for example. And then we get an estimated Hessian matrix and estimated parameters. We can then sample using MVR norm many different samples from this multivariate distribution. And then we can calculate predicted probabilities pi star, and you will see that it's a vector because it's for each of those sampled beta values we have a new prediction. So we have a long vector of m, in this case 100 predictions, and then we can look at, for example, the standard deviation or the quantiles of this distribution and so forth. We can look at different aspects of these sampled values. So we can just plot a histogram to show the uncertainty.